We've heard a lot about platforms, and just in case you were wondering, we're done with that. We're not. We're going to hear a little bit more in this next talk. And our speaker is the former Vice President of Corporate Research at KUKA, where he led research and technology development for robotics products, services, and solutions for almost 2 decades. Since 2004, he's been playing a leading role in European robotics by coordinating impactful research studies and by founding 2 major leading European robotics associations, Europe and Eurobotics. Please welcome on stage Managing Director of Intrinsic Germany, Dr. Rainer Bischoff. Hi, Rainer.
Thank you, Max.
Great to have you here.
Thank you.
Here you go.
Thank you. Good afternoon, everyone, and happy local time to those of you who are watching online. Rainer Bischoff, I'm the Managing Director or General Manager of Intrinsic in Germany, and I would like to explain to you today what we are thinking of platform, and especially of an AI-integrated platform for intelligent robotic solutions. I have a couple of sections in my presentation. First of all, it's an introduction to Intrinsic, so I think not all of you might know Intrinsic yet. And then what are the key pillars of a platform for robotic solutions? I will also present a couple of use cases where our platform is in use today, and also how we are going to create a strong ecosystem before I come to the conclusions. Introduction to Intrinsic first. We are a software and AI robotics company at Alphabet. Which means that we belong and have a strong arm in the back, financially and technology-wise. You see here a couple of companies or entities at Alphabet, Google DeepMind, Google Research, Google Cloud, and also Android as a platform. This is technology that we can leverage in our own platform. And AI, security, privacy, analytics, cloud, or container technology, this is something where we can learn from Alphabet technology and use this for our own platform so that we also don't have to reinvent the wheel when it comes to building this platform. We are also integrating or developing an ecosystem, and we are doing this with partners first. So our platform is not yet available for everyone to use, but we are teaming up with partners, and the ones that you see here, like Trumpf, Siemens, NVIDIA, Comau, and Keba, have been the first ones to adapt the platform with their technology and for their solutions. You also see a little logo ROS here. I will come to this in a minute. Our platform addresses many customer roles along the value chain. So you only have a platform when you can actually cater for many different roles. So if you start on the left-hand side, these are the asset builders that develop assets. And assets can be hardware, this can be robots, this can be sensors, this can be cameras, but it can also be software assets. These assets form integral parts of the solutions. And to build these solutions, we have solution builders and solution installers. We are trying to separate these 2 roles of a solution builder and a solution installer, which are today mostly formed by system integrators. But we explicitly want to create a new role where actually developers can just build digital solutions that are then bolted to the floor and integrated on the shop floor by solution installers. And of course, finally, there's the end customer with a problem, with a challenge that has to be solved. So they use these robots in the operations. Maybe to give one quick example here, so Comau is a robot manufacturer, so they would count as an asset builder, but Comau also has a big system integration business, so they're also a solution builder and solution installer, actually. And when you go a little bit higher up in the Comau universe, there's Stellantis as an automotive company that is a big end user of robots, preferably from Comau. So that's why we also selected Comau as one of our first innovation partners in recent years. What are now pillars of a platform? And this is also very general. It's not applies to our platform, but to our platform not in particular. This platform needs 4 strong pillars. The first pillar is developer tooling. So you need tools for developers to be able to develop these assets, and you need tools for developers to build solutions. This is one thing. The second pillar is powerful AI capabilities. So you need something for a platform that people really want. And this is today AI technology on the shop floor. So it's advanced, reusable robot behaviors that increase the flexibility on the shop floor. So it's perception skills, pose estimation, it's collision-free path planning. It's also machine learning-enabled motion skills. The third pillar is an infrastructure. Every platform needs an infrastructure so that you can actually build these assets. In our case, it's container-based infrastructure, so that with each asset is embedded into a container that can be upgraded, that can be sold to other companies. And the fourth pillar is that we are agnostic with respect to hardware, with respect to the robots that we are controlling, and it's a real-time controller that we're actually offering. So one of the strengths of the platform in the end, especially in robotics, has to be that you are able to use sensors and especially sensor reactive control. And this is enabled by our fourth pillar here. The fifth pillar, the ecosystem enablement, this is something that can come later. So today, we do not have a marketplace yet where people can freely exchange or transact solutions and technologies. It's more like a catalog-based systems where people are integrating their technologies in catalogs that can then be used. So the first software that is based on our platform is FlowState. It actually allows you to develop a solution from design to simulation, to debugging, towards deployment and operation, all in one browser-based environment. It is targeting to the solution builder that is building such a solution. You can access it from any web browser remotely. Also, what we said today, what is very important, you can collaborate. It's very important that you can collaborate along the roles that I mentioned, but also within one company. You can easily combine motion perception and sensor-guided capabilities. What you see here is a no-code or low-code UI. You can also use Python or you can use C++, so there's different ways to access this platform. And with the click of a button, you can go from a simulated world to a deployment in the real world and back. So with this software, we are already able to build production-grade solutions with some of our early adapters. And the three screens that you see here on the left-hand side, this is where you actually build the application. This is a flowchart-like environment where our customers said they really enjoy this. So like Sumitomo earlier today also had this kind of flowchart representation. Each of these blocks is a skill. Can be motion skill, can be perception skill, and you can have also the logical things that you see here. What is also very important to make it work is a digital twin. So you need something that actually represents your hardware and the behavior of that hardware. And then on the right-hand side, the scene graph or the catalog from which you can get the elements that you need for your solution. What's now important about AI? AI comes in many different facets. And these facets are actually difficult to use by today's shop floor operators or even by developers of these solutions. So what we want to do, we want to make AI integrated in the platform so that it's much easier to use. Simple machine learning for vision or for motion skills is already integrated. The others in yellow, this is something that is coming up, that is in the R&D pipeline, reinforcement learning, using large language models or generative AI and foundational models. And artificial general intelligence is something that is really coming later. Our platform is catering to all levels, from the cloud to the edge to the actual real-time embedded software. And this is then allowing us to, or our customers, to build these solutions. And I give a few examples. So what we believe what is really needed for a more flexible, more accessible way to program robots and to use robots is first of all perception. What you see here highlighted is detection of the 60 pose of objects in very cluttered scenes at different difficult lighting conditions. This is something where we can really reliably extract the 60 pose as a precondition to handle and grasp these objects. The second capability that is needed is automatic collision-free path planning. You see here like a ghosted robot that is actually the planned robot on the way towards assembling something here. And the third thing is to actually use the robot controllers of today and extend them with sensor-reactive skills. Some more examples here that you see what kind of objects can be detected reliably and with high precision. And this is an example from the Comau example that we built, where you really can, based on a CAD model, detect something reliable in 6D space. We are also working on foundation models. Actually, I thought that's a video. Can you maybe click on the video that this is running through? Okay, you would have seen a couple of pictures of renderings like this one, where you can actually see that under difficult lighting conditions, you can even detect these metal, shiny objects in space, and all that is needed is a CAD model. But we are also working on foundation models, where you have already CAD models of like 100,000 different workpieces and train with synthetic data, and then adapt it also with real data to make it possible with only one-shot learning to detect these kind of objects in space. So this is something that is in our R&D pipeline, so not yet available, but is very important to have these kind of technologies available to simplify programming and solution building. And then what is also important is that these more complicated AI technologies are still easily programmable not maybe by a shop floor operator, but by someone who has been trained on using, let's say, this kind of flowchart-based environment. So how do we make AI accessible and usable? We already had mentioned this already. It could also be that the actual programming is assisted by AI technology, so to make it simpler to actually come up with this graph in the first place, having intuitive UIs. AI has to be ready to be used out of the box, so you don't want to configure too many things in order to make an AI function work. Perception, planning, and control are among the first skills that should be realized. Then you train AI with real or with synthetic data. Both is important. And in the end, it's not about training or learning to control a robot end-to-end from pixels to talks, but it's important that you're able to reuse and reconfigure skills so that you have this kind of decomposition of a solution into skills where each individual skill are able to reconfigure. And then in the end, whatever kind of AI you use in your development phase, it should, of course, also work in the operations phase during runtime. I mentioned ROS in the beginning. So in the beginning of 22, we actually acquired Open Robotics. Open Robotics wanted to join us because they were seeking for more sustainable funding to develop ROS, Gazebo, the simulator, and OpenRMF. It's an open source fleet management software. Brian Gerke was leading that effort. He's now our CTO, and we are building our platform and flow state on top of it with the 1.3 million ROS developers in mind that we have today. So that is something where we actually build bridges to the ROS ecosystem, which will still continue to thrive. I was also at ROSCon earlier this week, so it's a really very good community where many solutions and many pieces of technologies are coming out that can be used for future solutions. Not everything will be developed by one company or by one university. It's actually together we are building this ecosystem. And that is one important bridge to achieve that. What is also coming out of such an effort is that actually many more developers will be able to program robots. So it's AI experts, it's developers that just are software developers and have no clue about robotics yet. It's definitely the roboticists or simply computer science graduates that are able to work with this, and engineers. And the developer tooling, as I mentioned, intuitive GUIs, Python or C++, you need to think about simulation, digital twins, and in the end, how to make large language model applicable to come up with these applications. On the infrastructure piece, our software is based on a real-time operating system, and on top of that is Kubernetes. That's a kind of container software. We can orchestrate these containers. I mentioned containers already as a basic ingredient or the basic encapsulation of our skills. There's a lot of services in the cloud that are needed for a browser-based experience like we are offering, and it's really instrumental for the approach that the digital twin and the real world are accurate and exact. A couple of use cases. Just as a reminder again, what we are building here, and sorry for the broken fonts here. It was good when I submitted it. So we are providing the engineering suite, some of the capabilities needed, the infrastructure, and we make sure that all the upgrades and updates are actually working. That is something where people, of course, in the industry are today very afraid of, that we want to change running systems. So I very much agree with Jens, what he said before. So we want to change running systems to be able to upsell more technology at the lifetime of the robot, to be able to enable high mix, low volume scenarios, which is a difficulty today. And then there's the solution builder and installer who use these tools to build an automation product, who are owning it and who are also owning the end customer relationship. So we are not changing that. So the solution builders and installers will work with their end customers to directly sell the solution. And they can take from the catalog of the assets the components they need, the cameras, the grippers, the end effectors, or compute. And here's one example. And I can assure you the video was working before. Can you try to make it run? Because otherwise it's half the fun. So we are working with Zotac and Robomotion as two of our partners. Robomotion is a company that is building flexible robot work cells. And Zotac is a company who builds on top of that digital solutions. And so Zotac was programming this robot work cell of Robomotion for the machine tending of an injection molding machine. And again, reference to Sumitomo here, but it was an Arborg injection molding machine.
Excuse me, Rainer, we're trying to get the video to work in the background. So as soon as it does, we'll let you know, okay?
Yes, I can. Yeah, I will see it here as well. So what then the solution engineer of Zotac was saying when he first experienced flow state, it's so much easier for me now to develop a robot program because I don't have to do this tedious teaching of points in this very tight enclosure of an injection molding machine, because it's all done automatically once you have this digital representation of that injection molding machine. So he was very happy with it. In a few minutes, he was able to program what was taking before a week or so. And that is something where we can really accelerate the development phase, but also have a way to react to sensor information during the runtime. Should we wait or? Yeah. I was basically already finished with that slide, but just to give people an impression. So you have, here's a digital twin of the cell, and you see, this is, for instance, it's a KUKA Agilus robot, and it's working in a very tight environment of that injection molding machine. Here to the left, you see then the flow chart with the skills. The green ones have been successfully executed. The purple one is the one that is currently being executed, and then the gray one, which are the ones that are still upcoming. When you double-click on a skill, you can configure it. Yeah, that's the machine in real. And thank you for making the video work again. Okay, I think I can go to the next slide. And this was with sound.
Designed using an offline phase, and from there you calculate all the programs. Intrinsic is merging these two worlds. You have a simulated environment. You can actually program the process, even check if the process that you are programming is right or not. And on the other hand, you can read from the reality and update the simulation process. This is really new for our sector, and this is really effective.
I just wanted to have this quick testimonial from a Comau engineer, so you can see the full video here at that link. It's also provided with the handout. It's important for Comau that they, as a solution builder, are able to use this working on a solution in a digital domain before they actually go to the real domain, and that there's no deviation between the simulated and the real world. Finally, a little bit on our R&D pipeline and collaboration with 3 parties to create this ecosystem. As I said, the software is not yet freely available, but we are partnering up with a couple of companies. For instance, Google DeepMind. I mean, that's an obvious thing that we are doing this within Alphabet. But what you probably know from the Nobel Prize winner, they were using this AlphaFold to detect these protein chains. And a very similar technology can actually be used to do automatic collision-free path planning for multiple robots working on one car body here, which is here simulated. This is very cool technology. It allows you to bring down the development time by a factor of, I don't know, 100 or 1,000, because it's only a couple of hours in the cloud rather than people programming these robots with offline programming systems today. And during execution, you also have some kind of flexibility. Second example, very quickly, so you can run, so what Google DeepMind is doing, they're also running on our platform, and then they are training robots to actually open these kind of bottles, as just one example, with a tele-operated system, and later use this to do reinforcement learning to actually do what you can actually see here. And then second example, more industrial use case. This is a task board where the robots are assembling gears, and this has also been learned and used by Google DeepMind. This is not available in the product, but you see in a direction it would go if we can enlarge this ecosystem with contributions from third parties. And it just doesn't have to be Google, it can be any university, any startup who does not want to or should not invest money in building up infrastructure, but trying to make their value add available on a platform. Another company we are cooperating with, of course, also NVIDIA, using here an example use case from Trumpf, where it's important to pick these sheet metal pieces where the suction cups should not actually suck through the holes. So this is something that has been also trained with a foundation model. And then in the end, it was possible to generate the grasp points for these arbitrarily lying sheet metal pieces, detecting them, and moving the suction cups in a way that you could actually pick up these pieces and stack them on the other side. Okay, final slide, conclusions. With our platform, we try to operationalize AI. And only when we make it available for developers of solutions and also developers of these kind of assets, then it will become valuable in manufacturing. So we are creating this platform to make AI-enabled solutions possible for everyone to access, to build, and to operate. And I would also like to stress this can only be done together. So we are definitely not alone in this effort. And this will only then us enable to unlock AI for robotics solutions, and then in particular for millions more of developers, entrepreneurs, and businesses, and not for the handful of nations or companies that we have today that are using robots. Thank you.
Thank you very much, Rainer. Sorry for that, for technical issues. We can play the first video as well, if you want to.
All good.
Okay. In that case, we can squeeze in one question, I think. So if there are any, please put your hand up. And as usual, we'll pass the microphone round. Does anyone have anything for Rainer? Yes, here at the front. Thank you.
Thank you for an interesting presentation. You mentioned that it's very important that there is no difference between the simulated world and the real world. And I agree to that, of course, but it's...
How to make it true?
Always a little difficult to make that happen. So what are you doing?
Yes, so you can actually feed back from the perception of that cell into the digital model. That is one thing. And the other thing is, because we are depending on not on taught points or frames in the scene, but on behaviors of the robots or skills, it is becoming a much simpler problem, actually.
So the skills are more intelligent than just moving between A and B. Is that it?
It's not just a blind motion, it's always a motion that is based on the digital twin, but you make it accurate in those places where you actually need it. You probably don't need it in all the places. And of course, if someone's installing a metal rig in a cell that is not modeled, then there's nothing you can do, right? So we are definitely limited then.
Thanks.
Okay. That's all we have time for. Rainer, maybe you'll be available during the next networking break. Thanks again,
Happy to.
Rainer Bischoff, everyone.